Hello, Algebra 2 students. I appreciate you finding time to get your notes taken care of. Today we're going to look a little bit further into growth and decay. Last time we spent a little time looking at incremental growth and decay, which is when something happened kind of almost on a schedule as a certain amount of time went by. Today we're going to look at continuous growth and decay, which is when things kind of happen on an ongoing basis, not a scheduled amount of time goes by. Things are just continuing to happen. Okay, so copy down the title, Continuous Growth and Decay, as well as the objective, which is to apply exponential equations in order to solve problems of continuous growth and decay. As always, press pause anytime you need more time to get something copied down, and then press play when you're ready to move on. Okay, so let's take a look. Now this is the same as yesterday. You don't necessarily need to copy this top part down, these examples, but remember we're looking at exponential functions, which do help us with a great number of everyday type situations. We talked about population expansion and declination, interest accumulation, both for you and against you, chemical decay, growth, stuff like that. Now, where you need to be copying down is here. If the change occurs on a continuing or ongoing basis, the formula that defines such changes is, and the formula, as you can see, looks a whole bunch different, or not, I'm sorry, not so much different as the formula that we saw yesterday as far as its structure is concerned, but we do have a lot of new variables and pieces of information that are going to go into this formula, including a constant that is probably new to many of us. So let's take a look at these variables one at a time real quick. A, okay, I left this in its original format, same as yesterday. A represents the initial amount. Now, if you look this formula up on the internet or textbooks or anything like that, you're liable to see it using different variables other than the ones that I'm using here. I've done the best I can to leave the variables the same as they were last time, representing the same type information so as not to confuse you as much as possible. So A still represents the initial amount of whatever it is that we have going on. The next variable that we have is the constant that I was talking about earlier. Okay, it is E. Okay, you've probably seen it on the face of your calculator. You might have even run into a problem maybe in a science class from time to time that has utilized E. Well, E represents Euler's constant, and Euler is a mathematician, of course, from back in the day, and he came up with this particular constant, and it's directly related to exponential relationships. And E is an irrational number, much like pi is, meaning it is a decimal point that does not ever terminate or repeat. Okay, and its approximate value is 2.81828, and you can look it up if you want to. Again, it's irrational. Those decimal points never stop. In general, people usually think about E as being in the ballpark of 2.82. However, there's no reason to round it off like that. It is a button on our calculator. Our calculator knows the entire value. Okay, so we can simply use that rather than rounding off and typing in an incorrect decimal point. The next variable is K. Okay, and K is officially what's referred to as the constant of proportionality. Okay, well, the constant of proportionality, its function is to basically relay to the problem not only whether the problem is growing or decaying, but also by how much it is growing or decaying. So some basic properties of K are if K is a number that is greater than 0, meaning it's going to be positive, then the problem is growing. Okay, so if you see a positive exponent, that is growth. Okay, and if you think about that, if it's a positive exponent, that means x is positive. The graph is not turned around backwards. So as it goes from left to right, it is going from horizontal to vertical. That is showing growth. However, if k is smaller than 0, that's going to relay to us that we have a problem that is decaying. And again, that makes perfect sense, because if k is negative, that makes x negative. And if x is negative, that causes the graph to spin around backwards, which means it's going to be vertical on the left side, but horizontal on the right. So that's a problem that's actually getting smaller. X still represents time. Okay, X is always on. Of course, the x-axis, the horizontal axis, when time is part of the problem, we know time always gets the x-axis. Okay, so if time is an issue in the problem, it will get x, so that should hopefully make sense to you as well. And then lastly, the variable y, or the function y, represents the amount that is remaining in the problem at however much time has gone by that you are looking at. Okay, so a lot of information there as far as in understanding what gets plugged into the formula. But after you get used to the formula and its different variables, it's really no big deal to understand it and to work with it. Okay, so let's take a look at a few examples here. We're going to start off again looking at population expansion. You're going to find that a lot of the topics that we can use this formula for are some of the same topics that we used the incremental formula for last time. And the only difference between one formula and the other, I mean, other than the way the formula is built, is one is done as a certain amount of time has passed before a certain thing may happen. This is assuming population expansion where the population is undergoing constant change, okay, where it's growing all the time, not just at a particular time. Okay, so let's take a look at an example that might go along with a continuous population expansion. A bacterial culture reveals that a population of 250 cells continually expanding at a rate of 3.1% per hour. Sorry, I think I've got a grammar issue in that first sentence. Sorry about that. But anyway, what is the population at the end of one day? Well, the problem with this one compared to yesterday is when we were talking about like rodent growth. Obviously, rodents can, the population growth only happens at certain times. The mouse has, or the rodent has to become impregnated and then deliver its little litter of babies in order for the population to grow. So it happens every so often. A bacterial culture, it's not like it's giving birth to new bacteria. The bacteria are simply growing and expanding at all times. As long as they have nutrients to expand, they will continue to expand. Okay, so let's see if we can't put this into the formula. Again, this is a continual growth. Okay, so we're using this new formula, y equals a times e to the kx. Okay, well, A represents our initial population. That is the 250 cells that the problem refers to. E is Euler's constant. That's that 2.81828 irrational number. Okay, we will simply access that on our calculator. And then K represents our constant of proportionality. This is the part that we really need to understand. Okay, positive K will tell us that our population is growing. Negative K would be a population that is shrinking. This is going to be growth, so we want to make sure that K is positive. Okay, and we have 3.1% as our growth rate. Now, of course, remember, percentages do not go into problems. Decimal points go into problems. So 3.1% will become 0.031 when we plug it into the problem, moving the decimal point over 2 spaces to the left. That's going to be our growth rate, 0.031. So that's going to be K. And x represents the amount of time that has gone by. And of course, we're only talking about one day, okay? But the problem is in terms of hours, the rate of 3.1% per hour. So when the problem says one day, we need to make sure that the formula understands that one day is 24 hours. Okay, so that's what our formula should look like. 250 times the constant E to the 0.031 times 24 power. Okay, now this is a matter that goes straight into the calculator, and if you have issues with how to type this in, that's definitely something that you want to ask about. Okay, but in the end, you're going to get a decimal point back out of this, and what we get is we have a result of 526.08 cells. Okay, so in 1 day's time, this bacterial population has more than doubled itself. Okay, and that's the relationship. That's how continual expansion works. Okay, let's look at another. Compound interest. Again, we talked about compound interest a little bit yesterday with the incremental growth. Okay, and as long as the increments are in a certain period of time, after a month the interest compounds, or after a week the interest compounds, that is incremental. But there also are situations where the interest is constantly being recalculated. Okay, so values are being calculated and re-input into themselves. Okay, so there's a difference between what we looked at yesterday and a problem like this one. Okay, a high school graduate gets a greeting card from her grandmother. Inside is a deposit receipt for $100 into an account compounded continuously at 10% interest. Now, the girl, and she's going through graduation, lots of stuff going on, blah, blah, blah. She forgets about it. Okay, she forgets grandma gave her the $100. And then many, many, many years later, she is putting together her will and making sure all of her affairs are in order. And they come across this account and they go, hey, cool, 57 years later, okay, she's got this account. How much money is in the account at this point in time? Okay, so let's take a look at it again. This is a continuous compound, okay, continual interest, which means this account is constantly undergoing calculations of interest. That $100 is being looked at, and fractions and fractions and fractions of pennies are constantly being added to it. Now, it sounds like that would be a ton of money in a big hurry, okay, but you got to realize we're talking fractions, very, very small fractions of pennies that are going back into this account. But those fractions of pennies are then earning interest of their own. Okay, so after 57 years, where does this thing end up at? Okay, so it's a continual problem. So we are looking at the y equals a times e to the kx. Okay, our initial amount, of course, is the $100 that Granny gave us. E is Euler's constant. K is the constant of proportionality. Okay, we're getting 10% interest. Okay, well, that is money, that's positive money coming back to us, so that will be a positive zero 0.1 will be our constant of proportionality, changing 10% into a decimal. And then X will be 57 years. Okay, so our problem will look like this guy. 100 times E to the 0.1, that's our 10%, and times 57 years. Okay. Now, after 57 years, $100 grew into $29,886.74. Kind of puts it in perspective. I hear people a lot of time going, it's only $100. I'll just go to the mall this weekend and spend it. Well, maybe you want to put it in the bank for a little while. Yeah, it might turn into something more than a mall trip. Okay, one more. And this is probably something that you have talked about or heard about a little bit in chemistry over the years, and that is the topic of half-life. Now, just to refresh your memory, a little bit of background there, half-life is almost exactly what it sounds like. Some chemical compounds decay over time, and half-life is the measurement of how long it takes a particular chemical or element to decay to half of its original amount. Okay, how much time goes by for the chemical to decay to half of its original size. Okay, so a lab has a 120 gram sample of radium-226. That is a radioactive isotope, very hazardous. Okay, so this radioactive isotope has a half-life of 1,620 years. If the constant decay of rate is negative 0.0004, how much of the sample will be left after 100 years? Okay. Well, now 120 grams, that is not very much at all, not a very large mass or anything like that. Okay, so let's take a look at how much of this radioactive material is still around after 100 years of it hanging around the lab. Okay. Now, obviously the radioactive isotope is not going to wait a certain amount of time and then suddenly decompose and become a smaller amount. So this is happening on a continual basis. So we will use the formula for continuous decay. Y equals A times e to the kx. Our initial amount, as we've already said, is 120 grams. So that's going to be our A. E is the value E. Okay, and K, that is our constant of proportionality. This time we are decaying, so it's going to be a negative number, and we were provided that number as negative 0.0004. Okay, very small, very close to zero, but it is negative, so it is diminishing the problem. And then X is 100 years, the amount of time that is going to go by. Okay, so the problem would look like that right before it goes into the calculator. 120 times e to the negative 0.0004 times 100 power. Okay, now you're going to find out how come radioactive material is such a problem. After 100 years of having this material around, it has decayed from 120 grams to 115.29 grams. So not even 5 grams of it are gone after 100 years. Now, if you're wanting to know what that is in more standard weight, 1 gram is approximately equal to 1/5 of 1% of a pound. So we're talking 0.002 pounds is 1 gram. And we did not even get to 5 grams. So we're talking about 1/100th of a pound of this stuff decayed after 100 years of time. This is how come they're so concerned with how radioactive waste is disposed of, because it obviously just does not go away very quickly on its own. Okay, so hopefully you can see the difference between how continual growth and decay differs from periodic growth and decay. Obviously, the formulas are different, but so the big challenge will be knowing when to use which formula, and that's just a matter of you reading the problem and deciding, yes, time is going by in both instances, but with one, a certain amount of time is going by and then something happens, and the other one is, yes, a certain amount of time is going by, but this thing is happening continuously as the time goes by. Anyway, I appreciate you finding time to get your notes taken care of, and I will see you in class.